So, well, yesterday I discussed curvature, and before curvature I was talking about oscillating plane. So, there are some other important points that I forgot to mention about the oscillating plane. You see, yesterday we found that the equation of oscillating plane at a point r 0 is given by r minus r 0, r 0 dash and r 0 double dash equal to 0. Now, I can rewrite this equation of oscillating plane as r minus r 0 dot r 0 dash cross r 0 double dash equal to 0. Now, this vector r dash cross r double dash now is known to us. It is in fact this vector is in fact r dash cross r double dash is actually the vector b, because this is t and this is parallel to n, and t cross n is parallel to b. So, if you do not say it is parallel to b. So, the equation of the oscillating plane will become r minus r 0 dot b equal to 0. If we look at the equation of the oscillating plane in this manner, we will say that the oscillating plane is one which remains orthogonal to the binormal. That is, oscillating plane is the plane orthogonal to binormal. So, this is the property that we can identify our oscillating plane with, and this also means what are the three vectors? The three mutually perpendicular vectors are t, n and b. All of them are unit vector and they are mutually perpendicular to each other. If something is normal to b, then definitely that thing will contain t and n both. So, the plane will contain t and n. So, this also implies that oscillating plane contains t and n, the principal normal and the unit tangent. And these two vectors are being orthogonal are linearly independent, and therefore, I can think that oscillating plane is generated by t and n. So, this further implies that oscillating plane is generated by t and n. So, many a times we visualize the oscillating plane of a curve at a point as the plane which is generated by these two known vectors t and n. And now, similarly, I can think of the other planes which are generated by n and b or t and n. So, on this line we can think of the planes. So, let me rewrite down this observation over here. So, oscillating plane. So, this becomes a remark. The oscillating plane is generated by unit vector t, unit tangent t and principal normal n, and its equation is at a point, its equation at a point r 0 is r minus r 0 dot b equal to 0. Now, we think of other planes. So, similarly, a plane generated by principal normal n and binormal b is given by the following equation. That equation I can write down at a point r 0, in fact, r minus r 0 dot t equal to 0. If something is generated by small n and small b, its equation must be like this, and this being generated by two normals, we will call it a normal plane. This plane is called the normal plane. This plane is called the normal plane. Thirdly, we can consider plane generated by T and B. So, the plane number 3, the plane generated by T and B is given by r minus r 0 dot n equal to 0. Okay. So, we can easily see that this plane is generated by T and B, and therefore, n is orthogonal to the plane, and this plane is known as rectifying plane. This plane is known as rectifying plane. So, to every point of a curve, we not only have the 3 mutually perpendicular vectors, there are 3 mutually perpendicular planes also. So, they are also important. All right. Now, we can move on to the other notion, that is the torsion. So, yesterday we had considered a regular curve r equal to r s. First of all, we defined what is the curvature at a point of the curve. It is given by, it is in fact nothing but the rate of change of the tangent. When you move along the curve, the tangent change. So, the rate of change is in fact the curvature at a point, and this can also be written as r double dash. All right. Now, if you are interested in computing it in terms of the component of the position vector, so you remember the component of a position vector are written as x, y and z. All of them are functions of s. So, this can also be written in terms of the curvature, in terms of the component of the position vector. So, this is the derivative of double derivative of r. So, these components must be differentiated. So, second order derivative of x with respect to s whole square plus d 2 y upon d s square whole square plus d 2 z upon d s square whole square. So, straight away you can compute the curvature of a curve at a point by computing the derivatives of the components. Okay. Now, let us start about the torsion. So, torsion of a regular curve or a space curve. Torsion of a curve. Now, you see, if you have a plane curve with you, then you can easily notice that every point of the curve, the binormal will remain the same. There will be no change in the binormal. Suppose I have this plane and there is a curve drawn in it. So, whatever point you choose on the curve, the binormal will be the same unit vector, it will not change. And if I want to observe the change in the binormal for a plane curve, it will be simply 0. And therefore, the change in binormal will occur only in a non-trivial space curve. So, in fact, we define the torsion of a curve as the rate of change of the binormal. Okay. So, in fact, it is the tendency of the curve to go out of its oscillating plane. If you look at the helix, you will see if you choose the neighborhood of a point, you will see it will not lie in any plane. It will go outside the plane. So, this tendency of a curve to go out of its oscillating plane is called its torsion, and that changes from point to point. So, as in the case of curvature, we will compute the torsion also at every point of the curve. So, first of all, we straight away define the torsion of a curve as the rate of change of the binormal.
So, torsion can be calculated only for space curve?
Yes, for plane curve it will be 0. Okay. So, this is the definition of the torsion. The torsion of a curve r equal to r s is the rate of change, is the absolute value. I will consider the absolute value, is the absolute value of the rate of change of binormal. That is, let me denote the torsion by the symbol tau. So, this is the absolute value of the change in B. So, derivative of B with respect to s is denoted by B dash. So, this is our definition to begin with. Okay. So, an easy observation from here is the torsion, this is a point to be noted down, the torsion of a plane curve is always 0. The torsion of a plane curve is 0 at every point. In fact, this is a characterization for a plane curve. A curve is a plane curve if and only if its torsion is 0 at every point. Okay. All right. Next, we come to the expression of the torsion. Yes, curvature characterizes the straight line, torsion characterizes the planeness of the curve. Okay. All right. So, before coming to the expression, let us see, do we have some other thing? All right. Now, look at the derivative of b dash, because the absolute value of b dash is the torsion. So, let us see what b dash is as a vector, what is its direction and its magnitude, etcetera. So, look at b dash. So, b dash will be what? You see, b dot b, this is something we know. B dot b is 1, because it is a unit vector. Is it visible? Yes. So, differentiating it with respect to s, differentiating it with respect to s, the above relation will give me b dash dot b equal to 0, and this would mean that b dash is a vector which is perpendicular to b. Now, you have a triplet of vector t, b and n, and there is a vector b dash which is perpendicular to b, and therefore, it will go into the plane of t and n. Now, let us see whether what about b dot t. So, this is observation number 1. Now, we also know that also we have b dot t equal to 0, because they are perpendicular to each other. I will differentiate this also. So, blue, let me try blue. So, differentiating again, differentiating this with respect to s will give me what? It will give me b dash dot t plus b dot t dash equal to 0, or I can say that b dash dot t plus b dot t dash we know, t dash is r double dash and r double dash is k n. So, this is k n. Now, this is a vector parallel to n and which is perpendicular to b, and therefore, this dot product will be 0. So, what you get from here is that b dash is perpendicular to t. This is observation number 2. Now, what you see that b dash is perpendicular to b as well as it is perpendicular to t. So, it has to be parallel to n. So, these 1 and 2 imply that b dash is parallel to n. So, 1 and 2 imply that b dash is parallel to n. If I write down, that is b dash is something alpha times n, where alpha, now since n is a unit vector, so mod alpha must be norm of b dash, where alpha equal to norm of b dash or mod of b dash, and b dash we have seen is tau. So, in fact, so what do you get here is that b dash as a vector equal to tau n. Okay. We consider a minus sign from our side for convenience only, because there will be computation which will involve minus sign. So, we will take this scalar as minus times tau, where tau is the torsion of the curve. So, this is another important relation that we have. Okay. Okay. Now, with this understanding of the torsion, we can move for the expression of torsion, expression for torsion. Okay. So, what we do for the expression, now if you look at the first relation and this one, you can see that tau, that was equation number 1. Okay, let us call it 3. Okay. So, from 3 we get tau equal to minus time b dash dot n. Okay. This follows from here, you take dot product with n in both sides and you get it. So, this is minus times n, I will keep as it is, and b I know is t cross n, and I have to take its derivative with respect to s. Okay. So, this becomes minus times n dot, the derivative of this cross product will be t dash cross n plus t cross n dash, and you know here that t dash is k n. So, this becomes the product of k n and n, cross product of two parallel vector will be 0. So, this first term will goes off. Okay, so, what you get here is minus times n dot t cross n dash. Okay. Now, this I will simplify. So, I would like to express all these terms in terms of the derivative of r. So, the left hand side is tau, and in the right side I have minus times, in place of n I can write down if what is n, r double dash upon k. There were certain formulas which I did yesterday, and that was r double dash equal to k n. Okay. So, n is equal to r double dash upon k. So, these things are known to us, and then dot product with, you have t cross n dash. So, t means r dash cross n dash. What is n dash? N is equal to r double dash upon k. So, I can compute n dash from here. So, n dash from here, this is the quotient of two functions of s. K is a function of s, at a point it is a number, but globally on a curve it will be a function, differentiable function. So, this is k and this is r triple dash and minus k dash into r double dash divided by k square, or you can also rewrite it as r triple dash upon k minus k dash upon k square into r double dash. So, this is the derivative of n with respect to s. Substitute this value over there, you have r triple dash upon k minus k dash upon k square r double dash. Okay, now consider this cross product. So, this is minus times r double dash upon k dot, this becomes r dash cross r triple dash upon k minus k dash into r dash cross r double dash upon k square. Okay. Now, you consider the dot product of these two vectors with this. So, when I will take this product, it will be a scalar triple product. So, this is minus times r double dash dot r dash cross r triple dash upon k square, and then plus k dash upon k square. This is not a vector. So, now you have r double dash dot r dash cross r double dash. Now, the second term in this expression is 0, because you have a scalar triple product in which the vector r double dash is repeating twice. So, in a scalar where k cube, sorry, k cube, you are right. Okay. So, anyway, it does not matter, this is 0, because r double dash is repeating in this scalar triple product. So, this term goes off. Now, you just reverse the order here. So, minus sign will go off and things will be in cyclic order. So, I can rewrite this as r dash r double dash r triple dash scalar triple product, and this whole thing is divided by k square, and this is tau. So, this is an expression for curvature in terms of the derivative of r. Okay, this is formula number 4. So, this is the expression for torsion in terms of the derivative of r. So, we will use it as a formula whenever we will be given the equation of a curve in natural parameter, this formula will be used.